It's inconclusive. Okay, so now we could do integral tests. I think a U sub should, well, let me see. Yeah, U sub would work. You just have to separate this. Hold on a second.
I tried that. It was going back to 0. And because I did, I pulled the 6 out and I separated that.
Well, yeah, I think the integral of 2 over NQ would be a pain. If I try to keep it together, it would not, I would not have that plus 2. I'll have plus 6. I don't know, let me see. Let's try it out and see if I'm just gonna do some side work real quick. Oops. Sorry, that's at the bottom, not the top. Yeah, there's no way I'm gonna get 6n squared plus 2. If I multiply by 2, by 6, by 2, I would get, yeah. So it would be a complicated integral. It would not be an easy U sub. So meaning I do not want to do integral. So we'll do comparison test.
I have a suggestion. Maybe it's wrong. We couldn't split this this summation to be 6n squared over the whole denominator plus 2 over the whole denominator, and then we can solve it this way.
We can, and this part, that first part would be an easy integral, but the second one would be still a pain. 2 over n cubed. Yeah, I don't see
the other part would be going to 0 anyway without integral going to 0, because 2 over infinity is gonna be 0, so we can ignore it or no.
No, we can't. Until we would have to integrate first and then see what's happening.
Okay.
So you would have to do maybe like a partial fractions or something. So you'd have to figure out how to factor this, or maybe do something else. So it would get weird pretty quick. So I would recommend like a comparison or a limit comparison. So let's see here. So I know that my AN
is going to be 6n squared over. So we're going to split that, like you said?
No.
To do the comparison?
No, I'm just going to, we got to pick a BN. What would you suggest for a BN? That's the hard part, right?
I would go to
6n squared over n cubed plus 6n? No.
Well, we want to choose something that's helpful. So this is what I'm thinking right now. See how the degree of the top is 2, the degree of the bottom is 3, right?
Yes.
So this is, if they were to cancel out, let's pretend, right? Let's pretend it was only this. It would be 1 over n, right? Basically.
Yes.
So I'm going to choose to compare to 1 over n because it's kind of similar. Now.
Okay. Can you explain that one more time? That's why I'm getting lost. Well, how do we choose? Because you're saying n squared over n cubed.
Yeah, because when this goes to infinity, right, the rest doesn't matter.
Correct.
So really, we're only looking at n squared over n cubed, which is,
Okay.
you see what I mean? Because these
Yeah.
are the powerful. These are the most powerful degrees. So all this doesn't. When we're talking about infinity, this crap doesn't matter. But of course, I can't just cancel. That's not real math, right? But when we talk about infinity, we can kind of ignore this a little bit and think about, okay, well, I'm really looking at something over n. So I'm choosing this and hoping that it works. I don't know if it's going to work yet, but I'm going to try doing direct comparison. So the first question is, which one's bigger?
Would it be AN? I mean, right?
I think so. Let's see here. Yeah, it would be AN. Let's go ahead and graph to be sure, because I'm 90% sure that's true. It's not enough for me. So let's just pretend we have y equals fraction 6x squared, right, plus 2 over x cubed plus 6x plus 7. Okay, then I have y equals 1 over x. So, as n goes to infinity, it looks like the red one is bigger, right?
Yes.
Maybe not at the beginning, but after this point, it will be. So I know Bn diverges, correct?
Yes.
Do you remember why? Right, this is a divergent P series, correct?
Yes.
So since AN is bigger than BN and BN is a divergent P series, then AN also diverges. Let me double check this. That was number 17.
I thought it converges.
Yeah, let me double check. I think I forgot something. Seventeen. Yeah, it's diverges. Do you remember the picture I drew you, right, for direct comparison? By the direct comparison test. You could also do limit comparison, and that would also work.
When we do limit comparison, we separate them, right? 6n squared over.
You divide these two, and you take the limit.
Could you show me that, please?
Yeah, let's do it. But this method makes sense first, though, before we move on. Do you remember the comparison idea?
I remember the graph from the notes we were talking about.
Yeah, let's draw the graph again. So Bn is smaller. We agree with that, right?
Yes.
So we don't know what the heck An is doing. Could converge. I don't know. But I know Bn, we knew by Bn diverges because it's a Pierce series with p equal to 1. So if this one diverges, but it's smaller, then this one cannot come back down, right? Because this is the bigger one. So that means they both diverge. So since this diverges and An is bigger, that means both have to diverge because of this idea. Does that make sense? Like, there's no way this would go down. If it goes down to converge, that would imply that An is bigger, but it's not. So it's impossible. This tells you this must diverge. Does that make sense? Or
So long as they don't cross, they diverge.
yeah, so
But if they cross,
the easy way to think about it is if Bn is smaller and diverges, then An diverges.
okay.
Okay, I'll make you a little note here until this picture makes sense in your head. If Bn diverges and Bn is less than An, then An diverges because of this theory here. Number two, if An converges and An is smaller than Bn, well, let me write it the other way, sorry. If Bn converges and Bn is bigger than An, then An converges. So that's what you're looking for.
Okay.
Okay, and then that's how we build the pictures to understand these rules. Okay, but these are the requirements to make these conclusions. Now, if Bn diverges, but it's not the smaller one, then it doesn't tell you crap. It doesn't tell you anything helpful. If Bn converges and it's a smaller one, I'm like, well, that doesn't tell us anything either. So it has to be exactly like this, one or the other. All right.
All right.
Now, limit comparison. We'll make the note here, alternate method. Limit comparison. So you take the limit of An over Bn as n goes to infinity, which would be the limit of 6n squared plus 2 over n cubed plus 6n plus 7 times n over 1, right? When you flip it over. As n goes to infinity, this would give us the limit of 6n cubed plus 2n over n cubed plus 6n plus 7. What is this limit going to be?
One half. Well,
Yeah, it's going to be 6. So what is the rules for limit comparison?
if six is a if
Yeah, and the limit had to be something specific, right?
If 0 is less than 1,
Yeah, let me pull that up for you. Limit comparison. We said if L is finite and positive, then both converge or diverge. So our limit is finite, right?
yes.
So that means that both AN and BN must do the same thing. But what does BN do? Right, we already know what BN does. That's why I chose it. So BN diverges, and since the limit is finite, that means AN and BN both diverge. So since the limit of AN over BN is equal to 6, then both AN and BN diverge by the limit comparison test. That makes sense? So both comparison tests work. Integral test is technically possible, but it's going to be an ugly integral, and you're going to have to figure it out. I'm not sure which method would work though. I do not recommend it. Do you have any questions on this first one?
So, but if, okay, so that's all we have to do right there to solve it, to show our work.
Yeah, so you just write down the requirement since the limit is finite, and I mean, I ran out of space, but you would say since the limit is finite and Bn diverges, then that means both AN and Bn diverge by the limit comparison test. That's what it says in the notes in the book.
Okay.
That's a rule for limit comparison. But I think direct might be. I mean, either one. I think they're about the same in this example. Okay. Let's do another one. Number 18. Find the series radius of convergence. Okay. So when you're doing radius of convergence, you're going to use Reuter ratio pretty much all the time. And I see a power of n, so I'm going to do root test right away. So root test says you take the nth root, well, you take the limit of an with the nth root power. So let me write that better. So an is equal to x minus 1 to the n over 2n plus 5. So the limit as n approaches infinity of the absolute value x minus 1 to the n over 2n plus 5. So I'm going to write as 1 over n just for the hell of it. Okay. Then that would become n power to the 1 over n two n plus 5 to the 1 over n, absolute value. All this must be less than 1, right? So these will cancel, and this will go to 0. So this bottom part will be just a 1. So when you take the limit, well, let me show one more step. When you take this limit here, this bottom part will become a 1. You guys see that?
It will become, well, it will become a 1.
Because the power is going to become a 0, right?
Yeah, 0 is 1.
Oh yeah, anything power 0 is 1. Yes, got it.
So when you take the limit, you're left with absolute value of x minus 1 less than 1. So then you remove the absolute values and solve for x. So add 2 to both sides, or sorry, add 1 to both sides, or I guess all 3 sides, and you get your interval of convergence. So what is the radius?
It's 2.
Radius would be 1, no? Yeah. Radius of convergence. They did not ask us about the interval. If they did, we would have to test the endpoints. So I'm gonna cross that out. Even though it's kind of right, it's not finished, but they didn't ask for it.
Very quick question. Why we say r equal 1? I know the interval, how we get the interval. Why we said r equal 1?
The radius of convergence is 1, right?
Okay, because it's falling between 0 and 2.
Mm-hmm.
Okay.
Right, because the diameter would be 2, right?
Yeah.
Okay. Next one's the same deal. I would recommend root test as well. So let me see. 18 was this one. Let's do 19. Well, I'm sorry. 20. Let's do 20. 20 has a this is interval of convergence. So we're gonna have to do this piece. Okay. Send the fourth. Let's do a ratio just for fun. So AN is x minus 2 to the n over n to the fourth 2 to the n. AN plus 1 will be x minus 2 to the n plus 1 over n plus 1 to the fourth 2n plus 1.
It isn't x minus 4 to the n?
Number 20 is x minus 2 here.
Okay. All right. So,
And the an plus 1 at the lower part between the bracket n plus 1 power 4?
Yeah.
N plus 1 power 4, okay.
Yeah, this is a 2, and it looks like a z. Whatever. Okay. So the limit as n approaches infinity of an plus 1 over an is equal to the limit as n approaches infinity of x minus 2 n plus 1 over n plus 1 to the fourth 2 to the n plus 1 times n to the fourth 2n over x minus 2 to the n. That must be less than a 1. Okay. Let's see how this is going to go. So that would be x minus 2 to the n times x minus 2. N plus 1 to the fourth times 2n times 2 n to the fourth times 2 to the n over x minus 2 to the n. Okay, so this cancels with this cancels with this. So now we have the limit as n approaches infinity of x minus 2 times n to the fourth over 2 times n plus 1 to the fourth. Now, when you take the limit, these are both degree 4, right?
Yes.
And when you take when the degrees match, you're left with just the coefficient, right?
Yes.
So when you take that limit, we're going to end up with x minus 2 over 2 less than 1. Remove the absolute value, multiply by 2 everywhere, add 2. So this would be my interval. But we still got to test it.
What did we add to?
Oh, because of this 2 right here, minus 2.
Okay.
Okay. So we need to test the endpoints. So at this point, for convergence. So we're running out of space, so let's go to the next page. So I'm going to plug in 0 and 4 into the original here, and then find out if those converge. So here we go. So let x equal 0. So the series, x minus 2 to the n over n to the fourth, 2 to the n. Okay. That would be negative 2 to the n, right? When you let x be 0, that's what we would get. Now I'm going to pull out the negative n. So how would you, so this is my new series when x is 0. What test would you use, or how do you start?
The limit test.
Yeah, you can do the limit test, but also you take the absolute value, right? And get rid of the negative.
Yes.
To test for absolute convergence. So check for absolute convergence. In other words, test this one. So what is this guy doing? First of all, these are going to cancel, right? You agree?
Yes.
N to the power 4 at the bottom, right?
Mm-hmm.
Okay, yeah.
And what kind of series is this?
The P series?
Series.
No, it is
No, you're
the
right.
geometric series.
It's a P.
It's a P series.
Mm-hmm.
Yeah, because 1 over n can be all power 4, right?
Yeah. So if it's 4, what does that mean?
It's even.
True. But what does it mean for P series?
It's greater than 1.
Yep, it is greater than 1, so that means,
Conversion.
yeah, this converges. So at x equals 0, we have a convergent P series. So now I know it's going to be 0 comma something. What is it, 4? So the interval, this is what I'm trying to figure out. I'm trying to figure out if I put a bracket on both. Right now I know for sure there is a bracket on 0. All right, so now I need to show my work for 4. So now we do let x equal 4, right? What do we get?
We cancel the n square and the n square up and down, right? Or no? We already canceled them.
On this one, yes. This part, yeah.
Oh, okay.
But this one as well, right? So when I let x be 4, 4 minus 2 is 2. So now they cancel again. So it's the same thing, isn't it?
Yes.
So at x equal 4, we have a convergent P series again. So now I know bracket on the 4. Okay. So the interval of convergence is 0 to 4 with less than or equal to, because they're brackets. And the radius of convergence is, what is that, 2? No.
Yeah, 2, right?
2, right? Yeah.
That's 2.
Okay. So when they ask for interval, this is what you have to do. You got to first step, right? Start from the beginning, because there was a lot going on. First thing is apply when you see interval or radius, you need to use the ratio or root test. So you do your work, and then eventually you end up with an interval. But we don't know what's happening at 0 or 4. We just know in between we converge for sure. But we need to test 0 and 4. So now we go, okay, let's test the endpoints. So you let x be 0, x be 4 inside here. So that's what we did right here. So x is 0, giving us a -2. I factor out a -2, cancel my stuff, and then I did the absolute convergence idea. Because I know if it converges absolutely, then for sure the alternating will also converge, right? Looking at the rules for absolute. So absolute gives me this, which is a P series, so that means we converge absolutely at 0. Then we let it be 4, and we end up with this, and it converges when x is 4. So now I know that we put equal to. Is there any questions on this problem?
No, not number one.
Okay. All right, let's look at some Taylor problems. Let's start doing some of the Taylor problems. This is 22, I think. Find the Taylor series. Generated by f at x equals a. So f of x is 1 over x. A is 7. So what we did is find the derivatives, right? First derivative is going to be what? Negative 1 over x squared, right? Second derivative would be positive 1 over 2 over x cubed. You know what? Let me show the work. So that would be 2x negative 3. 3 derivatives would be 2 times negative 3 times x to the negative 4. 4 derivatives would be 2, negative 3, negative 4, x, negative 5. And technically the first one had a negative 1, right? I just didn't write it. You see that?
Yeah, going the power.
Mm-hmm. Okay. So now we got to plug in the value of 7. So f of 7 is 1 over 7, right? F prime of 7 is negative 1 over 7 squared. Double derivative of 7 would be 2 over 7 cubed. Third derivative, sorry. Okay. That would be 2 negative 3 over 7 to the 4th. Fourth derivative of 7 would be 2 negative 3 negative 4 7 to the 5th. All right, so now we're going to create our pattern, right? So the formula for Taylor is fn derivative at c, which is going to be 7 for us, times x minus 7 to the n from n equals 0 to infinity. So the 0th term would be simply, oops, forgot the factorial. That would be
1. Right?
Yeah. The 1. No, hold up. I mean, there's no number there, but I guess we'll leave it. It's fine. 1 over 7th to the no, hold on. Yeah, okay, sorry. So it'll be 1/7 times x minus 7 to the 0 over 0 factorial. So the first one is positive, and it's minus 1/7 squared times x minus 7 to the first. First one. Okay. Running out of space already. 1 over 7 cubed times x minus 7 squared. 2 factorial. I gotta forget my numbers, right? I had a 2 on the top, right? For first derivative, no, that was right. Shit. This one had a 2. All right, so what is my pattern, right? So we got to take care of the alternating piece. So we're starting at positive. So -1 to the n. So when n is 0, it stays positive. So that works. Now the next piece I need is times 1/7 to the n plus 1. That way it stays 1 higher. Then I have x minus 7 to the n over n factorial. Now the number, what is the pattern that you see here? 1, 2, 3, 4.
Go up by 1.
Right?
They're raising up by 1.
So that's a factorial, isn't it? Right, this is 4 factorial. 4 times 3 times 2 times 1.
Yes.
This is 3 factorial. 3, 2, 1. 2, 1, 1. So we have a factorial on top. What is it? Is it n or n plus 1?
N plus 1.
Let's see here.
We're on the second.
0, 1, 2, 3, 4. No, it'd be n. N works. So there we go. Now we got it. So this will cancel, right?
Yeah.
So we're left with the series as n equals 0 to infinity of -1 to the n times x minus 7 to the n. Then this part can just be brought to the bottom, n plus 1, because these are going to cancel. So this is the Taylor series that represents the 1 over x when x is equal to, when a is 7. Is there any questions on 22?
No.
Okay, so yeah, you need to take the derivatives, you need to plug in the number that they give you, and you need to find the pattern, right? Once you apply the formula. So this fn part right here, that's from this. So I just plugged that in, right? X minus 7, well, that's just going along for the ride. Who cares? N factorial, well, that's just part of the formula. So then you look at this guy, and you try to come up, what is the summation, or the sequence that will create it? So then you put it all together, and you get this. So this will output these numbers. Now let's do another one. Let's do 23. This is Maclaurin, so it's a little bit easier. At least I hope it is. Find the Maclaurin series for the given function. And so they told us that the function is e to the negative 6x. And Maclaurin implies that a is 0. So first derivative would be what? Itself, right? Times negative 6. Second derivative would be another negative 6, but so 2 of them. Third derivative would be 3 6s, or negative 6s. Fourth derivative is going to be 4 negative 6s. Now, if I plug in 0, I get 1. First derivative at 0, I get negative 6. Second derivative at 0, I get 36. Third at 0, I get, what's 6 to the third power? I don't know what that is.
215.
215?
6 to the third, right? 216, I'm sorry, 216.
Yeah, 2 and 6, that's right. So this would be negative 216. Fourth at 0 would be
1296.
Yeah. 1296. Okay. So now we apply the formula. Let me bring it up because I forget what it is. So the summation of n equals 0 to infinity of f n at 0 times x minus 0 to the n over n factorial. So that would be 1 times x to the n over 0 factorial. Actually, sorry. That would be just a 0. Minus 6 times x to the first over 1 factorial plus 6 squared times x to the second over 2 factorial minus 6 to the third x cubed over 3 factorial. So what is the answer? What is this formula for this? All right, so let's take care of the alternating part. So it's plus, minus, plus, minus. So the first one needs to be just n, because a 0 will take care of it. Now I need the 6 part. 6 to the n, right? 0, 1, 2, 3. Yeah, this would work. X to the n works. 0, 1, 2, 3 should be n factorial. Let's see if that's an answer. Looks like B. Yeah, so this is our answer. Do you have any questions on 23? Okay. 24, this ain't crap, but we're going to do it just because it looks difficult. Okay, it says find the Maclaurin series for the given function f of x is cosine 2x. Okay, so Maclaurin again implies a is 0, right? So let's do the first derivative. What is first derivative of x, of f of x?
Plus negative sine 2x.
Yeah, but there'll be a times 2, right? Because of the chain rule.
Yes.
So we're going to have a negative 2. I'm going to put it in front, that way it's easy to see. Second derivative,
Cosine.
positive or negative? Does it stay negative?
No.
No.
Yeah. Okay.
It's going to be, derivative of sine is cosine, right? So it stays negative. But
Okay.
this part does not bring a new negative. Maybe that's what you meant.
Yes.
But this third one will bring a negative, so it would take it back to positive, right?
Yes.
So it'd be sine. And again, this will be negative 2, negative 2 cosine. All right, so f of 0 is, it's going to be what? What's cosine 0?
One.
Yeah, it's going to be 1. What is sine of 0? Right, this will be
0.
0. What is this second derivative at 0 going to be?
-4.
Yeah. -4. Triple derivative at 0?
+8.
But the sign would make it 0 again, wouldn't it?
Yeah.
Fourth derivative at 0. It's 16, right? 2, 4, 8, 16. Excuse me. So, yeah. Okay. So we'll apply our formula for Maclaurin. It's going to be f to the n at 0 times x minus 0 to the n over n factorial. So that will be, for the first one, it will be 1 times x to the n, or sorry, x to the 0 over 0 factorial plus 0 minus 4 times x to the 3, 0, 1, 2, 2 plus 0 plus 16 x to the 3, 4. So what is the pattern? What is the Maclaurin series?
Going up by 4.
Yeah, so we're going to disregard the zeros, right? Who cares? So let's only look at the pattern for the ones that are here. So the powers are going to be even, right?
Yes.
Yeah.
And we alternate plus, minus, plus. So let's start with an alternation. That takes care of plus for 0 and for 2, even. Nope. Right, that doesn't work, does it?
No.
So plus 1. Does that work?
Yes.
So 0 gives me 1. 2 gives me negative. 4. 4. 0, 1, 2. 4 would not work, would it?
Oh.
Nope. Maybe. What about plus 2? Does that work? 0. Nope. What about 2m plus 1? Does that work?
Will it work for the 0 though? Because it would make it a 1, right?
If it's 0, it'd be a negative 1 to the 1, which would be negative. Maybe this works. What about this one?
Yes, this work.
This works for the first one. And the second one, if I plug in a 2, I would get 4.
Plus 2, 6.
But it's not, that would be make it
No.
positive. Dang. Close, we're getting closer. 2 and yeah, sometimes we just gotta be clever. Let me double check everything. Maybe I messed up here. This is 1. Second one is negative. First derivative is negative, but it doesn't matter. Due to that, still negative. Third one zeroes out, so it doesn't matter. Yeah, it looks fine. I don't agree with the answer. Because the answer has -1 to the n. But that doesn't work, right? The bottom part's easy. Let's do the other parts for now while I think about it. This is 0, 2, no, so, oh, I see. I see, yeah, so I think I was thinking it way too hard. No, it is. We just treat this as 0 term, first term, second term. We just ignore the other ones. We just pretend they don't exist. Okay. See what I mean? So for 0, it's negative, right? It would make it, it would make it positive. For 1, it would be negative. For 2, it'd be positive, right?
Yes.
So yeah, it's fine. Then we have 4 to the n, because 0 is gone, first power, second power. And then 0 factorial, 1 factorial would be 2, second term would be 4, right?
Yes.
Times the x to the n. 2n, sorry, because we got rid of the odds. Yeah, that's it. Oh, sorry, something that takes some extra thinking, right? The only difference is they factor this into a 2. It's the only difference on the answer. So they went one extra step and said, this is 2 to the 2n. That's the same as 4 to the n. Okay. You guys have any questions on this last couple of problems?
I just got to go over them again. Look at the rules and all that.
Okay. All right, guys. Well, we'll stop here, and I don't know. Maybe I can. Well, I guess we'll see. I don't know where that we're on the schedule. Let me check. Schedule. Because we're on week 13 now. Only a 3 weeks left, including this one. So week 14. It's Thanksgiving week. So I'll start chapter 10 stuff on Monday, and we'll see what happens on Wednesday. Then week after that, we'll finish chapter 10 and start reviewing for the final. And then final exams. Okay.
And
We're just
the test is going to be open this week till Monday.
Yeah, I'll leave it open till Monday. Let me open it right now. If you guys want to take it tonight, you can.
There will be a review as well. Tonight, no, I'm just saying, is there going to be a review that we have to solve before the test, like every time?
There is a review, but I don't know if I have a requirement. I need to check.
Yeah, it usually couldn't. The test will not be open until I get 80% in the review. That's always the case. If you cancel the review this time, that would be great. No.
Yeah, I mean, so I did it with you, so it doesn't matter, right? So let me put due 23rd.
Also, I want to just do a kind reminder, a sweet reminder that there is 10 points extra credit for the final exam because of the quiz that we submitted. Don't forget it, because I'm hanging on them. My life is on these 10 points.
Yeah, I won't forget. I won't forget.
Thank you.
All right, so put your chapter 9 test is open now. And then let me see what the review says.
Yeah, it says you got to make at least an 80 on the review.
Can you open at all or no?
What, the test?
Let
me see. Yeah, it allows you to see it and open it, the test.
Okay.
I mean, not take it. It just allows us to open it.
Yeah, I think just ignore the thing that says 80%. I think you can start it. Just go, if you want to go straight to it, you can.
Okay. And this already shows my my extra time.
Oh yeah, let me do that for you too. I added more time in general, but I'll add extra just in case.
Okay.
And thank you. That will help.
Because I know that these problems take a while.
I gotta go back because the last couple of them, this last portion of the test was really giving me a
Oh,
run.
the Taylor.
Before the Taylor. The Taylor, I kind of get pretty good.
That's
It's just
good.
before the one before the Taylor, I was having to. It was giving me a run for my money.
Which one was that? The Power Series?
Yeah, the Power Series and the for some reason I get confused. You know, doing the comparison and the limit comparison.
Yeah, it takes some getting used to. Those took me a while to understand. Like I hated those. I would avoid it. But once you get it, they're actually really helpful and easy to do. Once you know how to do it, of course.
So I'm gonna do a couple of those more before I jump on the test.
Okay.
Alrighty.
Excuse me. All right, guys. If you have no questions, then we'll stop here.
Okay.
You have a good night.
Have a good night.
And the final is gonna be as a cumulative, right?
I think so. I'll let you know.
Okay. All right. All right, Mr. Gonzalez.
Yeah, let me think about that. But yeah, I'll get back to you.
Alrighty.
All right. Have a good night.